You trim a head of broccoli into perfect little trees, drop them into roaring boiling water, and walk away. 10 minutes later, you lift the lid. That electric green has slumped into something tired and gray, the color of an old army jacket left out in the rain. If you've ever felt a sense of culinary defeat looking into that pot, you can let it go. You didn't do anything wrong as a cook. This color loss is a predictable chemical reaction triggered by heat. The vivid color of green vegetable is not a permanent trait. It is a fragile, temporary chemical state, and the second that vegetable hits the heat, a clock starts ticking towards its destruction. To stop that clock, we have to look closely at the biological engine powering the color, chlorophyll. It's the pigment plants use to catch sunlight and bounce green light right back to our eyes. Chlorophyll is one of the most beautifully engineered molecules in nature. Picture a flat ring, a kind of molecular dinner plate. Sitting dead center on that plate is a single atom of magnesium. That one atom is the whole show. No magnesium in the center, no vivid green. Every gray, drab vegetable you've ever pulled from a pot is the result of that one specific magnesium atom getting forcibly kicked out of its seat. The magnesium is knocked off its throne by two specific threats. The first starts the moment your water temperature rises. Watch what happens as a pot gently warms up toward a window between 60 and 82 degrees Celsius. Right in that temperature band, an internal enzyme called chlorophyllase wakes up. A living plant uses it for ordinary maintenance, but during cooking, this enzyme works furiously to dismantle the green pigment. Slowly bringing a pot to a simmer traps the vegetable in this exact thermal window, giving the enzyme the time and temperature it needs to systematically break down the color. Low and slow heat works against you here. You're effectively leaving the pigment in the room with its own executioner. As the water hits a rolling boil, the heat ruptures the plant's cell walls. This releases a flood of naturally occurring organic acids that the plant normally keeps walled off in separate compartments. These acids unleash a swarm of positively charged hydrogen ions rushing through the wreckage. The center of the chlorophyll ring is their target. The ions swarm in, displacing the magnesium atom and taking its seat. It becomes a dull, brownish-olive structure called pheophytin. This atomic swap changes how the ring reflects light. It is the precise chemical transition that turns a vibrant vegetable into a muddy, drab one. This breakdown follows a predictable march. In plain boiling water, the acids need a specific amount of time to reach the magnesium. That cliff hits right around the 10-minute mark. You can see the endpoints of this timeline in your pantry. Flash frozen vegetables are hit with a quick blast of cold that pauses the clock. Canned vegetables, however, undergo intense heat for a long time, stretching that 10-minute cliff into an hour-long fall. The difference between the frozen aisle and canned goods isn't an accident of the product. It's the same chemical reaction dialed to two different extremes. To beat the reaction, you have to outrun the timeline. This is why we blanch. A short plunge into a rolling boil rockets the vegetable past the enzyme's danger zone so fast the enzyme is denatured before it can act. But the cooking doesn't stop when you pull the vegetables out of the pot. The internal heat means the acids are still working to strip that magnesium away. To arrest a reaction, you need an ice bath. Plunging the hot vegetables into ice water crashes the internal temperature, freezing the acid activity instantly. High-end restaurants use this combination of extreme heat and immediate cold to lock that neon green color in place. Preserving the internal chemistry of a plant requires thermal shock to violently outrun the clock. Heat is the trigger, but acidity is the master dial. The pH of the cooking environment controls the speed of the hydrogen flood. This is why you should dress a green salad at the last possible second. An acidic vinaigrette performs the exact same magnesium stripping action on the counter that boiling water does in the pot. You can slow the fade to a crawl by nudging the water toward alkaline. A pinch of baking soda acts like a chemical sponge, soaking up stray hydrogen ions before they can reach the magnesium. However, that same alkalinity attacks the pectin that holds plant tissue firm. You can buy a hyper-vivid green color, but the cost is a vegetable that quickly turns to mush. The green of your vegetables is a clock you control. By understanding the timeline of heat and the dial of pH, you stop guessing at the stove and start steering the chemistry.